Hi everyone. I'm Manasvi Goel, and I have been working at Sun on the Pond project with Jim Yana Osborne from Princeton and Amy Roberts from UC Denver. So the Pond project basically aims to make it easy to access custom format binary data, and this awkward target for Kaitai project is a significant step towards that. But before we dive into the details about this project, it is important to understand the need and motivation behind it. So, in order to analyze the experimental data, we need to be able to interact with this data. However, the data formats for scientific data often differ across experiments due to the specialized hardware and availability constraints. To interact with these unique data formats, custom data acquisition softwares must also be written and maintained to interface with the hardware and record any data to the disk. And once this data is saved to a file, the binary strings must be interpreted and translated into something that is readable by a human or a program designed for those files. Since the binary formats for scientific data are often unique to a particular experiment, researchers are solely responsible for developing, documenting, and maintaining these softwares, which are often tightly coupled with that particular data format. This increasing number of custom data formats has been a prominent challenge for the nuclear and high energy physics community. However, within the LHC experiments, this problem has largely been solved with the widespread use of root. However, they are not all experiments in the NF community use root for their data formats. We have experiments such as the Cryogenic Dark Matter Research, which is the CDMS data, which is basically a series of experiment designed to directly detect particle dark matter in the form of weakly interacting massive particles, and they still continue to use these custom data formats for their specific research needs. These binary formats are often only understandable by Fortran, which has its own set of complexity and limitations. Therefore, making this process of conversions of a custom data format into software analysis code simpler for the user while needing no changes to the existing data formats holds immense value for the broader NF community. So the one potential solution to this problem is the Kaitai Struct. For those who are not aware, Kaitai Struct is a declarative language that takes YAML-like descriptions of a data format structure and generates code in any of the currently supported 11 languages for reading a raw data file. The key idea behind that is that a particular format described in the Kaitai Struct YAML, the KSY language, and then it can be compiled using the Kaitai Struct compiler into the source files in the programming language of your choice. So this Kaitai Struct compiler code is written entirely in Scala, which generates the code for the selected programming language as strings in Scala. The generated modules includes the code for a parser that can read the described data structure from a file or a stream, and it can be included as a library in any of the external code. All these source files in the supported language generated by the compiler have the goal to be human readable. That's why they utilize an external layer of Stream API, which is followed by a Kaitai Struct runtime library of the respective language that the user is using. So let's break this down by taking an example of Kaitai. So imagine that we have a simple binary data structure that describes animal species, their age and weight for a zoo, and you want to analyze this data of some animals using Python. This data looks like this. So the data look like this. Here you can see where we have an animal entry for each animal, and in that particular entry we have the details regarding the length of the species name, age, and their weight. But the actual format of the binary is a slightly bit more complicated. And you can see an example of one such entry here. So in this, the first byte contains an integer value, which denotes the number of letters in the species name. The next n bytes are the ASCII values containing the species name. After that, we have 1 byte for the age and 2 bytes for the weight. The fields that are larger than 1 byte are written in the little Indian format, in this case, which is the weight. So if you don't have a hexstat handy, this entry is for a 6-year-old cow that weighs 1,500 pounds. So this entire data structure can be described in Kaitai Struct YAML, and the final KS5 file will look something like this. So in a KS5 file, everything starts with a meta section, which is where we specify the top level info of the whole structure that we are describing. There are two important things in the meta. First is the ID, which specifies the name of the structure. Second is the endian, which specify the default endianness. The license and the versions are something that is optional. With that out of the way, we use a SEQ element with an array, which is basically an ordered sequence of elements, which is used to describe which attributes this structure consists of. And each of these attributes have several keys, namely the ID, which is used to give the attribute a name, and the type, which designates the attribute type. We also have a option where we can add the repeat condition. So most of the real life data formats do not have only one copy of some element. We might contain several copies, and these copies like repeat the same pattern over and over. So the repetition might be either we have an element repeated up to the end of the stream, or we have an element repeated up to a predefined number of times. And we can also have an element repeated while there is some condition that is satisfied or not satisfied. So the Kaitai struct support all these repeat types. And if you want a better idea, if the KS5 file that you have written corresponds to your data or not, you can have a look at the Kaitai web IDE, which is, by the way, a great place to start with Kaitai. So in this, you can see that you have a section where you can write the corresponding the KS5 description of your data. And here you have the data described. And you can see if your data corresponds with the KS5 file that you have written or not in the object tree. So for our case, the object tree looks something like this. This KS5 file that we have written now, this can now be passed to the Kaitai Struct compiler by a command like this, where we have to use the T flag for specifying the target language that we want to use, in this case, which will be Python. And we also have to specify the path of the KS5 file. This generates a Python script called animal.py. And this Python script consists of all the classes and the functions that are needed to read the data that we have in the structure that we have in our KS5 file. And this generated code can be easily imported into any of the Python code for the analysis. And the output would look something like this, as we have seen similarly in the web IDE. So in this talk, we are talking about awkward target for Kaitai. So why do we even need Kaitai when we can just pass our data in using just Kaitai? So the animal.ksy that we saw was just a simple example. but the actual scientific data can be a million times the size of it, with even more complex structure. An example of this is the Midas event format, which is a variable length event format where we have this complex nested structure of events, which are used to distinguish between different events, and they use banks as the subsets of an event. And similarly, we can have different data formats which are even more complex and have more nested levels. So in such case, it becomes very difficult to decide how we can store this complicated structure, for example, in Python. And this will take a lot of human effort to do that. Besides, when we are dealing with large files and complicated data structures, even the most efficient Python code can be a bit quite time and resource heavy. That's where the awkward array comes into the picture. So the awkward arrays offer a powerfully dynamic and efficient approach to represent the complex data structures in NumPy-like arrays. Awkward arrays store the data in jagged nested arrays of arbitrary types and variable lengths, something like shown in this example. This makes awkward array an appealing target language for Kaitai Struct. Therefore, we have proposed using the C++ header-only layout builder libraries from awkward array to represent the data formats into NumPy-like arrays. If you want to know a bit more about layout builder and how to use it, you can refer to Jana Osborne's PyHEP talk, which was on Monday. And you can also have a look at the user guide in the awkward array documentation. So now, how does this awkward target for Kaitai work? Actually, it's pretty straightforward. A user just has to describe their data format into a case file, and they have to do this description of KSY only once for each specific format, which is the same as you would do if you are just using Kaitai. So all your effort will go into just writing the KSY files. All the code generation is handled by the Kaitai awkward runtime. So as you can see in this workflow, we have this binary data format that the users can describe in the KSY format, which will generate a KSY file. And this part of the workflow, which is generating the awkward code with Kaitai Struct compiler, which generates a Python module, is everything is done internally, and the user doesn't have to do anything. They can just like once they have the Python module, they can just load the data in the module, and then they have with the simple commands they get this Python module, and the exact details of it are still a work in progress. But this Python module can be then be imported, and we can pass our raw data files in that, and now you have your data represented neatly in the form of well-structured awkward arrays. So to elaborate that, let's take an example. So here is another example of a simple KSY file called fake.ksy, which is a bit similar to the previous example. And similarly, we have the name of the structure, which is fake, and we have all these sequence with ID and types. So we have the ID points, which is of point type. And in each of the points, we have three IDs, X, Y, Z, of unsigned int of 32 bytes. So let's take this example to understand how the awkward target language for Kaitai Struct works. So the steps are pretty simple. First, you have to clone the Kaitai awkward runtime repository if you haven't already. And then you just have to go to the Kaitai awkward directory. And then with a simple pip command, you can pass the your KS5 file as a CMake argument. This part is still a work in progress, and we are still figuring out how we can improve this for the user experience, and understand how the user will be using this. But for now, we have this pip install command. So how this works internally is that, similarly to the previous example, we the Kaitai Struct compiler takes this target language awkward, which is our awkward target language, as the flag, and then we pass our KS5 file, which generates the header and source files. One thing to mention is that the awkward code is written in C++. So we are using the existing target language that they have for C++ and STL, and we have modified it to generate the layout builders in awkward arrays. As I have mentioned before, that the Scala code is entirely, the Kaitai Struct compiler code is written entirely in Scala. So here's a snippet from that. So this is an example for generating the C++ strings for awkward, where we are describing the builder declaration for the record builders that we have. So here we have two functions, print structure and user-defined map, which are working together in order to generate the strings that we need in order to write the code for generating the definition of the record builder and the associated user-defined maps and enums that it needs for defining the field names. So if you see that here we have this out header awkward string stream, where like this is what we use to emit the C++ strings inside the Scala code. And for every language, the code is similar. So we are using this out header strings, and we just output the code that we need in order to generate the respective language. And the generated C++ libraries are somewhat similar to what it happens for the C++ target language, but the code for generating layout builders is combined with it now. So let's have a look at that. So here we have the header file, and we use these type aliases in layout builder, which are optional, but it is good to have. And then this is the builder declaration that I was talking about in the work code snippet. So this is how a record builder is declared, and we have the associated field names with that. And the rest of the code is pretty much similar to what it happens in the C++ target. We just have these data members for each of our builder types. The source file is a lot more interesting. So we have these user-defined maps for each of the sequence IDs that we have, and the corresponding types that they have. So like for each of the classes, we are setting the builder, setting the fields for each of the builder using the user-defined maps that we have. And we are using these the code that we have in the layout build, the awkward layout builder, for generating a list of set builder, and so that we can just start begin a list and end the list wherever it is required. And then we have this nested structure where we have the fake builder as the top level, and inside that we have the points builder. And similarly, we are appending all the data that is stored in these data members using the strings that we have generated from the Scala code. So after all of this, which is all done internally, the user doesn't have to do anything. You can print the returned ak.array simply in the Python shell. So you can import the module that you have and pass your raw data file into the load function. And then you'll have the generated awkward array, which is something like this for our example. But yes, this workflow is still a work in progress, and we are still thinking how we can make it simpler and more customizable. And we like right now it uses 5 and 11, but we are inclining towards C types. But yeah, that is still open to suggestions, and we are focusing a lot on improving the user interface, and we are also adding the support of index option arrays, as we found out that for certain KSY formats, we'll need that option. And that's it. If you have any questions, feel free to ask. And if you have any suggestions, please do so. And even after the talk, you can ask the questions in the Slack channel or email me or Amy Roberts or maybe Jim or Yana. Thank you.
Okay, thank you. And also, thanks for pointing people to the Slack. And are there questions now? Eduardo.
Hello. Hi. Very interesting, actually. I was completely unaware of the existence of Kaitai as well. So I was quite curious when I saw the abstract. I had one question. You mentioned at the very beginning CDMS as an experiment that is not using the format. So that calls for an obvious question, which is, have you been discussing this or maybe even collaborating already with a specific experiment to be a test bed for these developments, or for the moment you're still in pure development stage, and you then want to engage with some experiments or some collaboration, some team to see this in action?
Like I mentioned, Amy Roberts is associated with CDMS, so so the main aim of this project is geared towards the CDMS only, but we are building the project in such a way that any of the projects that have custom data formats can describe their data in the KS5 format and use this project in order to generate their data in the form of awkward arrays. So we are testing on the CDMS KS5 files that we have, but yeah, we are open to suggestions that if anyone wants to collaborate and want to see if their data format will be can be described in KS5, and then we can test it for our case.
Okay. Yeah, fair enough. Thanks. Yeah. I'm saying this. I think even some of the small experiments represented in this workshop, such as some neutrino-related experiments or double neutrinoless double beta decay and stuff like that. I think some of these experiments don't actually use root as a data format, so that could be an interesting application. Okay, thanks.
Yeah. Nikolai?
Yeah. So how general is this concept? Could I write something to read root files into awkward arrays? Sometimes that's actually also not so easy when they are more complicated.
Can you please repeat your question? Sorry, I couldn't hear it properly.
So I mean, sometimes even it's even not so easy to read root files, and so we have uproot for that, to read root files into awkward arrays. But yeah, if the data structures in the root files are more complicated, then this can be also challenging. Is this concept general enough that I could sort of generate such a Kaitai description
Mhm.
for some binary data within a root file, or I mean, at least within a basket of a root file or something like that?
Yeah, like if you have a binary data structure that can that you can describe in the KSY format, that will work the same.
If,
If
yeah, sorry. Okay, so Zana, we'll get to your question in just a moment. If I could add to that, KSY is very general. It might be possible to describe root in a KSY if you do not have any custom classes that require a streamer info. I don't think that KSY can learn new types from the file itself. I think that's a level of dynamism that KSY doesn't have. And another thing that KSY doesn't have is it doesn't say read up to a point and stop, and then read further and stop. Like when we're reading a root file, usually we want to read the directory and then let the user decide which file, which object in the directory to read, histogram or T-tree. And then after reading the T-tree metadata, then we wait again for the user to decide what arrays they want to read, what branches. And KSY only describes the format. It doesn't describe where laziness should happen. So that would be pushing it too far. KSY can't really be reading root.
Yeah, I mean, I meant more like, for example, like, could you use this as a replacement for awkward fourth? Like if we know for a particular branch type what the binary structure is, could we generate a Kaitai description for that and then use it to read the binary data only for that branch?
It could, although Kaitai makes code that needs to be ahead of time compiled, and the use case for awkward fourth is like a JIT compiler. So yes, you could, but you wouldn't want to. So Zana, you were next.
Yeah, I think I already find the answer anyway on my question. But anyway, I didn't get what exactly you want improved in your project. I mean, you told about the Python, and actually I didn't get like on the example with the animals. You just show that you wanted compiled your like binary data to some Python format. I don't know, and then on the fake example, like I don't know, it's somehow I don't know. Here you show like CPP examples, and I didn't get how the Python is related to that and what exactly you want to improve here.
Yeah, so like for this example, I just showed the Python, but you have these 11 languages that are currently supported in Kaitai. So this was just an example of Python, but you can do the same for C++ for animal KSY.
You wanted to improve this for all languages?
Can you please repeat?
You wanted to do I don't know, the comfortable, I don't know, user faces for all languages, or it was just example. I mean, it like you don't care what languages exactly to use.
So basically, like for the complex data structures, so that they can be presented in a well formatted, like something like awkward arrays, we are adding a different target language. Like they are already 11 languages, but we are adding another target language which will be awkward, which uses the existing the C++ backend for that.
Okay. Okay, I think I got it. Okay, thanks.
Bruno is next.
Hi, I just had a very simple follow-up question to the question that came before the last one, which was when we use, for instance, our data frame, sometimes it's a bit tricky to read nested loops. So I was wondering if this could support arbitrarily nested loops, or if this is in the plans.
For a binary data format, like if you have already.
Yeah, sorry, I mentioned loops, but I wanted to say vectors, sorry. So for instance, a vector, would this be supported in principle?
Yeah, I'm not sure about vectors, but like if you have a highly nested structure, like where you have a record inside a record and then another record, that is all that all can be handled with awkward arrays, and so yeah, that will be supported.
Okay, because that's interesting, because as far as I know, our data frame, for instance, doesn't support more than a depth of 2 or 3, at least last time I checked. Thanks.
Yeah, if I could add to that, the Kaitai can work with arbitrary nested things. So if you had some data that was like vector, 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 float, and we are currently using awkward fourth to do that in uproot, like Nikolai's question, that kind of data structure could be pretty easily described in Kaitai, vector, 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 float. But I think there's not really a connection to be made here between the format interpretations of either awkward fourth or Kaitai and the computation engine that is our data frame. Doing arbitrary computation is a different thing from reading arbitrary formats. They're kind of not in the same genre of literature, If there are any more questions about this, and this has been great, by the way, all these questions, they can go to Slack, because I realize we're 2 minutes past, and we should get to the last talk. So thanks again, Manasvi.
Yeah, thank you.